Hello everyone, welcome back to part 5.3 of the vulnerability research on the Linksys E1200 version 2 wireless router. In this video, we will be exploring how to set breakpoints on the HTTPD binary to analyze the strcat function and eventually investigate the stack-based buffer overflow vulnerability and how we can overwrite the return address to trigger a segmentation violation. So to quickly recap what we have covered in the previous videos. First, we perform static and runtime analysis of the HTTPD binary by using a few commands such as file and puntools checkseg. Followed by that, we performed source code analysis of the various functions involved in the vulnerability, such as the get merge IP address function, the apply CGI function, and eventually the validate LAN IP address function. From there, we were able to identify the required data parameters in the HTTP post request to eventually reach the vulnerable function. But first, I would like to discuss about the strcat function. So basically, this function is found in the get merge IP address function, which will write the value into the vulnerable buffer. So in the technical writer, I list out a disassembly from Ghidra and from GDB. So given that we set a breakpoint on this particular instruction over here, which is the delay slot right after the call to the strcat function. So for those of you who are not familiar with what is a delay slot in the MIPS or MIPS architecture or assembly, basically a delay slot is an instruction such as this, which appears after a call to a function. However, the values loaded or the actions taken, such as moving the value from V0 to A1, will be completed or guaranteed to complete before the first line of the called function is actually executed. Therefore, what this means in this case is that the proper value we expect to be loaded into the A1 register would be loaded right before the first line of the strcat function is executed. Also, this particular instruction over here, jalr, stands for jump and load register. So jump basically just jumps to the memory address stored in the T9 register, while LR, load register, basically just loads the appropriate return address value into the RE register. So what is the RE register? This basically stands for return address register. So looking at this line, SW stands for store word. It basically just stores the current value in the RE register into the memory address SP plus 96. So the plus comes from the brackets over here, while SP stands for stack pointer. So now you know that this instruction stores the value from the RE register into a memory address indicated by an offset from the SP. So what's the purpose of that? This is because when a function is returned from, we can see that the LW instruction, which indicates load word, instead would take the value from the SP offset, in this case SP plus 96, back into the RE register before a JR instruction would jump to the instruction identified by the RE register. Now, even that we set a breakpoint as mentioned before on this instruction over here, we would like to view the values in a few of the important registers. So as identified before, the instruction here stores the value in RE into the particular SP offset. So this SP offset value will be important for us later on to calculate the padding required from the vulnerable buffer into the start of the return address memory space, for which we can then overwrite the return address and cause a fault, particularly a segmentation violation, to indicate to us that we have successfully overwritten this particular return address. So following that, let's go down to over here, the call to the get CGI function. So as mentioned before, the line after the call would be the delay slot. So this basically writes the value S2 into A0. So in MIPS assembly, the registers A0 and A1 basically stores the first and second arguments respectively to the function. So in this case, it moves the value in S2 register into the first argument. So following that, you can see below would be the call to the strcat function over here, indicated by this instruction. Once again, delay slot, which moves the value from v0 into a1. So in this case, a1 would be the second argument, while the line before the function call would move the value from the S1 register into A0. So this over here represents the first argument. So now that we have identified and take a look at the important instructions, we can now go ahead and analyze the register values as stack pointer offset in memory space that we will further analyze when we set a breakpoint later on. So first, this will be array, which represents the SP+96 memory address space. Next, A0, which represents the first argument to the relevant functions, followed by V0. But why V0? So as we know before, right before the jump instruction, the value will have already been loaded into A0. So let's take a look in Ghidra for line over here. Yes, right before the call to the strcat function, the delay slot will write from V0 to A1. However, before that, the value from S1 would have already been written into the first argument. So therefore, only the A1 register will be affected by the delay slot. Therefore, in order to view the value in the A1 register, which is the second argument, we can reliably read it from the V0 register instead. So therefore, these two registers will give us the first and the second argument to the strcat function, while the S2 register would allow us to identify the CGI parameter name. This is because right before the strcat function, or a few lines before that, the jump to the getCGI function would be called, and this writes the value from S2 into A0. However, A0 would change when it is being called, when the strcat function is being called. Therefore, I've noticed that the S2 register, which will have stored the value into the first argument of the getCGI function, does not change throughout over here, as you can see. So from line 41F980, we can see that over here it writes S2 into A0. However, all these instructions over here right before the strcat does not modify the S2 variable. Therefore, this means that we could use the S2 variable to identify the value passed in to get into the getCGI function. So now taking a look back at Ghidra again, you can see that, as mentioned before, the getCGI function is called before strcat. So this getCGI function represents the function to retrieve the HTTP post parameter name that is written into the source variable before it is concatenated directly via the strcat function. Therefore, basically, as mentioned before, the S2 variable which stores the S2 register which stores the string value as the first argument to the getCGI would represent the data parameter name that we have to control in order to write the value directly into the vulnerable buffer. And as we know before, this likely represents the, over here, the LAN IP address 0, 1, 2, and 3, which will then be directly used to control the values returned into the vulnerable buffer. Now I'll be talking about GDB and GDB server. Supports GDB, which stands for the GNU debugger. It's a full-featured debugging application used by developers. However, for us, we'll be using it mainly for debugging the binary or the runtime behavior of the binary. While GDB server, on the other hand, is a lightweight program that acts as a remote backend for GDB. This is mainly used to save memory space on resource-constrained environments. So essentially, GDB provides the user interface and main logic. So usually we'll be running GDB on our more powerful or the main machine, while the GDB server would handle the low-level communication with the target process, particularly running on the device itself. And we know that the device itself is resource constrained. Therefore, GDB server would be very good for this use case. So do refer to my technical write-up to be able to understand how to retrieve the GDB server binary for the target architecture from this resource over here. And so GDB server, as mentioned before, would run on the target router. While we have to use the main GDB to connect to the remote target from our host machine. However, we have to use this particular binary, which is GDB multi-arch. This is because the normal GDB will not work since it does not support the MIPS architecture. So we can run this simple command over here to install the GDB multi-arch. So now let's head on to the terminal where I will quickly show you how you could transfer the GDB server binary from the host to the device. So over here I have the UART shell on the target device itself, while this will be the host machine, which is basically my Raspberry Pi. So as you can see right here, I'll list out that I have the GDB server binary over here. Quick file. Let's see that it's compiled for the MIPS 32-bit executable architecture. So going back, we're going to be using the wget tool over here to connect and retrieve the binary from our Raspberry Pi. But first, let's ping the, so basically 192.168.1.1 represents the target IP address. So we can see we can connect. While over here, you can see on this interface over here, yes. And config H0, yes, 192.168.1.35 would be the interface address of the Raspberry Pi. Okay, so first you have to run a Python 3 command to host a local server to be able to allow the device to retrieve the file. Now wget 192.168.1.35. Over here you can see running a port 8888. So retrieve the server and write it out into a temporary directory. After that, you can do a change the executable, change the binary to have execute permissions. Right now we can see that when we run the GDB server binary, it will work. Now that we know how to set up the GDB and GDB server environment, let's go on to setting breakpoints. So, okay, my technical write-up over here, we can see at the bottom. Anyway, I will be putting this link at the description below again. So, we will learn how to set up custom breakpoints on the binary. So you notice this is actually a workaround. Why? Even though GDB actually provides us with a feature to directly insert a breakpoint into the binary from the GDB interface itself, however, I have found that this does not work because somehow perhaps some kernel constraints from the device or something. Therefore, I'll be using a custom method to perform binary patching instead to set custom breakpoints, followed by using a manual stop signal to halt the running process for us to be able to perform runtime analysis. So now let's take a look at the command to perform the binary patching. For that, we'll be using the DD tool, which basically just stands for data duplicator. So to this tool, we're providing 4 arguments indicated over here. So first, OF. This basically just stands for the output file. So over here, let's see, write to file instead of standard output. Next, for BS, basically it just stands for the block size. And in this case, for us to read and write up to the bytes, which is the value provided, bytes at a time. So giving a value of 1 to this would make it easier for us later on when we are indicating the value to SIG. So next, SIG. This basically accepts the value memory address for us to identify how much to skip from the start of the binary. So to make it simpler, basically giving a value of 1 to the block size will mean that we can directly give the value of the memory address we wish to overwrite into this command over here. While lastly, for this argument over here, basically it just tells the data duplicator tool to prevent truncation of the data following the seek address. However, we have to pipe in using printf a particular hexadecimal string, a binary value that we want to write. So in this case, it will be this value, which basically represents the break instruction. Therefore, this entire command means to write the break instruction into the memory address of the TMP HTTPD binary. In that, we can modify the device to run the HTTP web server via our patch binary instead. So therefore, when we send the request from our host machine to the device, which is running GDB server, we will then be able to stop at the break instruction before sending the seek stop signal to allow us to perform runtime analysis from GDB multi-arc from our host machine. Okay, so now let's get on to the part where we actually set a breakpoint on the HTTPD binary and analyze the runtime behaviors using the GDB and GDB server setup. So as you can see right here, I have 3 consoles open on the device. However, from the UART shell, we are only able to actually gain access to 1 console. But in order for the GDB and GDB server setup to work, we need more than 1 console. So for that to work, as you can see right here, I'm using the dropbear SSH server. So you can refer to the link I have in the technical write-up, where I will show you how to connect to a remote server on your device via dropbear. And afterwards below, I also have some useful scripts that you can run to automate the process. But now just know that I'm using dropbear to serve a SSH server on 1 console and have the other 2 terminals connect to the server via a client for us to gain access to more than 1 console on the device. With that aside, now let's get on to the actual binary patching. So for this command, binary patching command, we'll be running it on the attacker machine, which is the Raspberry Pi, instead of console. Okay, so let's back to the technical write-up and copy this command over here. Paste it over here. Okay, so as mentioned before, this is the binary to indicate the breakpoint, while this over here indicates the file to look for the HTTPD binary. So for that, I have the binary over here in the current directory. So you can see now, say run this again. We can now let's point it the current directory VS1 seek. Okay, so this will be where we would like to set the breakpoint. So for that, I decided to set a breakpoint on the delay slot right after the call to the strcat function, which would be on this instruction. However, one thing to note is that the base of the memory addresses start from this address. Therefore, we have to minus it off from this value, which will give us the specific value instead. So copy that, and we can replace this value over here. And with that, we can run it. Also note that since we are running this command, this binary patching command directly on the provided binary itself, we should not perform this on the main copy of the binary itself, but rather a duplicate of it, which I have in the current directory. Now we can transfer the patch HTTPD binary onto the device. So let's go on to the console on the device and then use the wget command. So this is the address of my Raspberry Pi connected directly to the device. So if you're running, okay, so over here we have HTTPD binary. So you can use a Python 3 server to host a server to transfer the file. So port 9999, looking for the HTTPD binary, output it into the temporary directory indicated over here. Run it and change the escape permissions to this to give the HTTPD binary the execute permissions. Now let's view the current running HTTPD binary on the PID 325. So first we can kill it. Force kill is the PID. If you see that it stops running. And then we can run our own version of the patch HTTPD binary. As you can see over here, 1194. Clear the screen. Following that, so as shown before, we have the GDB server binary on our device. So you can use this command over here, attach it. Let's view the, as you can see over here, our patch HTTPD binary running on the PID 1194. Copy it. Then run the GDB server, attach it to the PIV indicated by this PID over here. Oh, so sorry, so I have to define where to run it, which will be 192.168.1.1, which is the address of the device itself on a particular port, for example 8888. Sorry, my bad. We have to define the IP address and port first before we actually define which PID to attach to. And with that, you can see attached to the PID 1194 and listening on port as specified 8888. So now we can use our attacker machine, which is our Raspberry Pi, to connect to this GDB server and perform analysis. Okay, so now let's connect to the device from our attacker machine. Also, previously I mentioned that you'll be using Raspberry Pi as the attacker machine. However, I'll be using another machine instead, which is connected directly to Raspberry Pi. Therefore, the Raspberry Pi will be acting as a gateway from the actual attacker machine to the device. So, also I have a port forwarding configuration from the attacker machine to the Raspberry Pi for the Raspberry Pi to act as the gateway. Therefore, anything we'll be running will be through the local host port, the ports forwarded from the local host on the attacker machine. So run GDB, Noti, Arch, set a few things, endian, little, set the architecture, clearly specify entire word architecture, MIPS. Set. Okay, you can see over here, target is set to little endian, the target architecture is MIPS, shell, clear. So now we can connect to the target machine using this command target remote, specify the address. So in this case, since I'm using port forwarding, I'll be specifying localhost and the port. But usually if your device, the attacker machine is connected directly to the device, you should specify the address of the device itself. So with that, you can see it's loaded, and over here, you can see that you will receive a message, remote debugging from the host on the particular port which is connecting from. Okay, see over here, it will load and show a context typical of the the GDB GEF. By the way, anyway, so yeah, shell clear to make it neat, and from there you can perform some analysis. But before that, we have to actually have a way to send the HTTP push request. But first, before that, okay, continue is for the HTTP binary to start listening. So basically, this attacker machine interface we have on GEF basically just controls the binary on the remote device. Sorry, the device, not really remote, but the device itself. Alright, now let's send the HTTP post request. So over here, you can get it from the technical write-up. So I'll be sending it from here. Go back to the main attacker machine. Okay. So, okay, I have it over here. Basically sending a request to localhost through the port forwarding to the variable apply.cgi function with the specified parameters and the authorization headers as what we have learned before. Okay, so what I would like to control is then IP address 0. I only give it a valid value. So let's make it 192. Oops, sorry, over here 168 given to len IP address 1. Len IP address 2 will be the value 1, and to len IP address 3 will be the value 2. So this basically sends the value 192.168.1.1. So you have to make these 4 parameter values valid, because if you go back over here and see, let's go back, where is the, yes, over here, in the validate len IP address function, right after get merge IP address function is called, there'll be a function which validates the IP address which is concatenated from our input. And if this is not valid, as from this if statement, I assume the function will be returned from. So therefore, we have to make it valid in order for the function to continue in a way that we will be able to test and analyze the runtime values. So I have found that if I were to give invalid values to the 4 parameters mentioned before, the server will respond with an invalid value or like error message, and this will cause the server to halt, and we will not be able to reach or successfully reach the breakpoint that we have set. But I'm not actually really sure exactly if this function over here is the reason why, but I've just found that we are required to provide valid values. So that's what I will do. Okay, so now let's run it. You can see for me too, no worries, it's fine. And to go back to the console on the device itself, read the config. Okay, PID over here. So what we have to do is to send a stop signal to it. And as you see, once I send the signal, GF should immediately show us the context or the runtime values basically. Run it. Okay, you can see stopped at the breakpoint, reason SIG stop. So now that we have stopped at the breakpoint, we can perform some analysis of the register values. So first, V0. So basically this x/s command given to GF or even GDB basically stands to print the value in the memory address indicated by V0 in the string format. So over here you can see at the memory address over here the value 192. So this is similar to what we have sent in our request. Over here as you can see, len IP address 0, 192. Okay, so what is V0? The V0 register basically contains the address that the return address from a particular function. So in this case, the function that is called before the strcat would be getCGI over here. So what getCGI basically does, as mentioned before, is to retrieve the CGI parameter value from our HTTP post request. And since you can see over here that it contains 192, this means that it has successfully retrieved the value, and we can actually control what is returned into this register. Next, PX. PX stands to print in hexadecimal format of the A0 register. So over here basically it just shows the memory address of the buffer that we can overwrite with the strcat function. Next, print memory address in string again of S2 register, shows that it is len underscore IP address underscore 0. So what is S2? So as you can see before, S2 in the delay slot after the getCGI function, right before the strcat, S2, basically the value in S2 is passed into A0, which means that S2 contains the first argument to the getCGI, which basically is the CGI parameter name that we have to control, which over here as you can see this confirms that we are correct because we have written it to the LAN IP address 0. So this provides us a confirmation that we are able to control the values in the specific registers, and this is important for us. Following that, px print in hexadecimal format of SP plus 96. So SP is the stack pointer plus 96. And you can see this value. And before I continue, I'd like to explain why actually I've used the value 96. So as you can see over here, this instruction basically means to print the memory address value from the first 10 instructions from the getMerge IP address function. So referring to this specific line over here, store the value, the current value in array, current value in terms of when this particular function is being executed. So store value in array into this. So basically this bracket means plus. So in this case, SP plus 96. So this is where the return address value will be stored at the start of the getMerge IP address function. So this particular address, calculated by, and once again, SP plus 96, is the memory address value that we wish to override in order to hijack the return address flow. So one thing that I would like to point out, however, is that if you notice, the value in AO, which is the buffer address, is at a higher value than the stored return address. So what this means that I'm not able to actually overwrite the value of the return address from our buffer. So why? Okay, so the common convention in the MIPS architecture is that the stack will grow from a higher memory address to a lower memory address, while values written would be written from the lower address to the higher address. Therefore, this means that any values or any memory address space higher than a particular buffer will be able to be overwritten. However, those that is below this particular buffer address will be physically impossible to be overwritten. In this case, since the buffer is at a higher memory address value than this, we will not be able to actually overwrite the return address value. However, in the later part of the video, I will show all of you how we can work around or bypass this stack layout constraint. So for those of you who are wondering, why are we only able to view the value to the first CGI parameter, which is 192, instead of those to the second and subsequent ones? The reason being is because, as mentioned before, we have set the breakpoint right after the call to the strcat function. However, this strcat function is executed within a while loop. Therefore, setting a breakpoint within the while loop will only allow us to break on the first run of the loop. Therefore, we are only able to see the first value. So let's say given that we want to actually break on the second, third, and fourth CGI parameters, there's actually a way to do it within GDB. However, in our case, it is sufficient and good enough to simply break on the first, as we are able to confirm that the values we write to the CGI parameter can be written into the vulnerable buffer. So now, let's set a breakpoint at a new location. So I have chosen to set it on this line over here, which is right after the delay slot, after the call to the getMerge IP address function. So as mentioned before, we know that the buffer we are able to overwrite is at a higher memory address value than the return address from the getMerge IP address function. So this is likely because the particular variable of buffer space allocated is within the validate LAN IP address function instead. Therefore, this particular buffer space exists within the local variable stack frame of the validate LAN IP address function instead. So just to quickly illustrate what this means. Okay, so referring to this diagram over here, the bottom, low memory address, the top, high memory address. So for now, you can just ignore this particular IOP, JOP gadget. For now, this will be covered later on in the next few videos. But anyway, so looking here, this is the stack frame of the getMerge IP address function, while this is a stack frame of the validate LAN IP address function. So what I mean by stack frame is basically just a particular portion of the memory of the stack allocated for a particular function. So this is automatically created by the program when particular functions, such as for example the getMerge IP address function, is called. So as mentioned before, the stack grows from high memory to low memory. So since the parent function of the get-merge IP address function itself is validate the IP address. Therefore, when the get-merge IP address function is called within the validate len IP address, a new stack frame which grows downwards towards lower memory address will be created. However, as mentioned before, the vulnerable buffer to the strcat function within the get-merge IP address function is actually a local variable within the validate len IP address function. Therefore, this particular buffer space is within the stack frame of the validate len IP address function instead, while the return address of the get-merge IP address function is at a lower memory space. Therefore, the values placed on the stack or returned to the stack will be returned towards higher memory space. So since we are not actually able to overwrite the return address of the get-merge IP address function, we can instead overwrite the return address of the validate len IP address function. But for that to actually work, we have to calculate the offset spacing between the buffer and the array. So therefore, we have to set a new breakpoint within the context of the validate len IP address function, which I have chosen to be on this line over here, D0, which is right after the delay slot after the call to the get-merge IP address function. So once again, you can refer to the memory layout which I have referenced previously in the technical write-up, which I have linked in the description below. There you can see the general stack layout of the functions involved for us to actually have a better overview and illustration of the layout. So with that aside, we can now set the breakpoint on the binary. So as mentioned before, on this line over here. So before that, okay, remember that I mentioned before that since the binary patching command actually overrides the binary that we provide to it as an output file, we should actually not run this on the main copy of the binary, which I have here. So previously I actually run it on the main or on like the binary name httpd. However, now I actually have ran a few more commands to rename it to label the particular breakpoint that we have set on. So therefore, using this particular binary now as the main copy, we should first copy it into a new location. And I'm gonna rename it as where we plan to set the breakpoint on. So in this case, this. Copy it. Sorry, no. Copy it. You can see now a new copy of it. And we will then run the binary patching command instead on the new file name, so as to not mess with the main copy of the binary. So yes, 285D0. And over here, specified as the seek command, the address we wish to overwrite. Running this now, we can see that it has been patched. So now we can go on to copy this patch binary to our device via the console. Once again, and just view the current one line. Okay, there's none. Okay. So it's again wget typically the address of our attacker machine on particular port which we host it. So on a Python 3 server 9999, on the directory we're gonna serve this binary. Okay, so copy this port 9999 9999 and specify the output, which will be somewhere within the temporary directory. Okay, retrieve it. Change executable of the httpd to 85d0. With that, we have copied the binary over to the device. So you see, we have seen that it's currently not running. So we can start it up with the new patch binary. Let's see now that it will start with a PID of 764. Now let's run GDB server. Once again, specify the resolution 8888 attached to the PID 764. With that, it'll be listening. So going back here, okay, let me just clear the screen. and run target remote once again to, yes, the port forwarded via particular port 8888. Okay, noise. Okay, yes. So I can see remote debugging from our attacker machine. And now we can see the context over here. Alright, so now let's get on to sending the HTTP push request. But before that, I would like to configure GAF to disable all these things that come out because it's a bit too much information. Okay, alright, clear. So now continue to have it run the server. And going back here, you can send the same push request to the apply CGI function with the data parameters, CGI parameters mentioned before. Okay, we can send it. Can exit from it to the matter. And going back, once again, we can send a 6-stop signal to the PID 064. There you can see it has been stopped somewhere within the validate then IP address function, which we have set. Okay, so now let's view the values in this stack. So let's run the command. There's scope L40 view 40 from the RSP, from the ESP, which is the stack pointer. With that, you can see the values right here in the stack. Okay, so now you have to identify where the buffer is relative to the stored return address within the validate then IP address function. Now, let's view the first 10 functions of the validate then IP address function once again. Okay, from here, you can see this is the location SP plus 132 where the return address is stored. So you can see the others is at SP 128, 124. This means that the array is stored at the highest stack pointer address, which will be somewhere below over here. So around the back, you can see a familiar address, which is 4225E8. So seeing that it starts from 422, this is very likely because the function, okay, so wait, this address or the array address, stored array address will be the return address back from the calling function, which called the validate len IP address function. So the function which called the validate len IP address function will be the apply underscore CGI function, which is within the memory address space of 422 and so on. So therefore, viewing all the values within the stack, this is the most likely one. And also because this particular value is at the highest memory address within the stack, which we have identified before, of where it is likely to be stored, this is highly likely to be the stored return address value. So to confirm that, let's just pick this out and we can view, let's say, 10 instructions from within it. Okay, let's perhaps go back for show the address is over here. Let's actually remove 8. Okay, so you can see within the apply CGI, which we have identified to be the calling function of the validate len IP address function, it jumps, very likely to be jumping to the validate len IP address function, followed by the delay slot. And this is where the validate len IP address function will return from after is being called from the apply CGI function, right after the jump and delay slot. Therefore, this value, 5E8 over here, is very likely to be the stored return address value. So now that we've identified the stored return address value, we have to identify where the buffer is. So remember before that we actually have wrote the value 192.168.1.2. Therefore, as you can see over here, this is the address of the stack which these values return to. So to confirm that, let's copy this and we can attack /s once again to view the memory space in a string format. Yes, and it prints that. While for this, copy this, can view 85x. Let's just view in, oh sorry, this, no, not this. Word. Sorry, yes. Okay, so basically, the memory space of this address, which is the address where our return address is likely stored. W just means word. It just basically means to print over here, yes, 4 bytes of values X in hexadecimal format, which is sufficient enough for us to see the value stored. So now we have to calculate the offset between the buffer we are able to write and this return address value. So let's restrict this TX in hexadecimal format. And also this over here. And we can minus it off. But for us to view it more easily, sorry, it's opposite. So this, once again, this from the stored return address value at the higher memory space minus the buffer address, which we are able to overwrite. And we change this to D, which just means print in decimal. We can see that the offset between the buffer or the vulnerable buffer returned to by the strcat function and the return address we wish to overwrite will be separated by an offset of 108. So now that we've identified the offset value between the vulnerable buffer and the return address to overwrite, we can now generate a payload to investigate the buffer overflow vulnerability. So as identified before, the offset is 108. However, notice that between each variable we control, it is separated by a dot. So the best way you can actually exploit this vulnerability will be to write overflow the buffer from the 4th CGI parameter. However, if you were to supply, let's say, a single value like X to the first 3 CGI parameter, this will end up in having 1, 2, 3, 4, 5, and 6. Therefore, our payload should have a offset of 102 because of 108 minus 6 to complement the first 3 values. So over here, I prepared it. So let's see, to the first address, let's give a value X, value X, value X. And only to the last parameter, which is len IP address 3, we will supply a Python 3 payload of 102 times A. And then, since this particular payload value will start to overwrite to the memory space right before the return address, we can supply 4 bytes of XXXX to overwrite the return address. So this should result in a segmentation fault. And if that happens, then means we have successfully exploited and overwritten the return address value. So for that, shell clear. Okay, continue once again. Sorry, 6 stop again. Okay, let's just... Okay, first we have to kill it. And then we can run it once again. Should be from within... Let's see, yes, wait. Okay, we can start it once again. That was the command. No, start here. 85D0. Yes. Rabbit 907 PID. Run this attached to it. Now it's listening. And you can connect to the remote target once again. Sorry, bear with me a bit. 88. Okay. Yes. Okay, give me a little while to load. Shell clear. Continue. And then we can send our payload within the HTTP push request. You send it. Okay, once again, send the stop signal to the PID. Now, you can see. Okay, so for now, since we have set a breakpoint, the segmentation fault will not happen. However, once again, if you were to view the... Yes, the stack pointer, we can see, from where we are actually able to overwrite x, yes, dot x, x dot bunch of a, and eventually overwrite the return address value is x text text text. So now let's run this. Start I. This basically just means to go on to the next instruction. It's not support. Okay, how about next I? Okay, you know what? Okay, there's some issues with the breakpoint. But anyway, next, we can once again, let's see, we can stop this. Okay. And instead run it from the main binary instead. This is the binary native on the device which have no breakpoint set. Run it. PID 920. Okay, run this. Once again, we can connect to the remote target. Remote target, okay. Shell clear. Continue. Send the same payload from the push request. Then see right off the bat, even without sending a stop signal, we receive a segmentation fault. Reason being because the program attempted to return to this address 58555. 5 basically just represents the character X which we have overwritten. Therefore, this tells us that we have successfully overwritten the return address value if an invalid value. Okay, let's view the belief. It's called the no, is that called RIP? Yeah, it's called RIP perhaps. No. Let's fill it in. Let's fill it in register specs. Okay, we can see that we should see value 585858. Yes. Sorry, I got a little bit confused with different architectures. By the way, yes. So array, the return address value which I mentioned before, which will store the return address from the end of a function when the function is returned to back to the calling function. In this case, 5558, which is an invalid address, thus giving the segmentation fault. Also notice that we are able to overwrite the PC, which just basically stands for program counter with the invalid address, similar to what we overwritten in the array. So a PC, program counter, basically is a specialized high-speed register within a CPU, blah blah, that basically holds the memory address of the next instruction to be fetched and executed. Okay, so with that, we have come to the end of this video on investigation of the buffer overflow vulnerability. So in the next video, we will go on to escalate this controlled crash into remote code execution. And we also find out later on that there are some issues, for example, such as back characters and all, which we have to work around in order for us to actually change the return address and use ROP, which is return oriented programming, which is a technique for buffer overflows, for remote code execution, along with return to libc, which I will discuss later on in more detail in the next video, and how we can use all of this to eventually give us remote code execution and basically a remote shell on the device.